We're going to talk about the physics of hearing, how we hear, and a good bit about the ear, and the scale we use when we talk about hearing and sound intensity. Um, so the topics covered in this include the parts of the ear, how we hear, that's all wrapped up in the parts of the ear. I've thrown in some auditory illusions for you so you can go listen to those and play with those. And then we're going to talk about the decibel scale. At the biggest piece, right, in the ear, the basic sound waves hit our outer ear and they go through the ear canal and they cause the eardrum right here, they cause the eardrum to vibrate. And that vibration then gets translated to the inner parts of the ear. Let's blow all of that up a little bit. So you've got your ear canal. You got to keep wax out of this. You don't want it to build up too much because why? If you have too much here, it doesn't, you actually lose some hearing, right? Um, Here are the parts that the cochlea here. So you go, okay, let me back up. Stay with my slide. The eardrum vibrates and causes this little structure here called the hammer and anvil to pound on that little bitty window. And that little bitty window then presses on the fluid inside the cochlea. And here you got the vestibule, and off the vestibule you have three semicircular canals, right? So it causes the fluid inside the cochlea to vibrate with whatever vibration you're getting out here on the eardrum, right? So you got your vibration on the eardrum, it gets translated into here. That causes those same waves to go around in the cochlea. And in the cochlea, there are very tiny hairs with nerve endings attached to them that feel all those little bitty vibrations. Here's the magic of the cochlea. Uh, It's kind of like a piano. And each of these little hairs along here are a different key, right? And so you go from bass all the way up to treble. And so one of the things you get on this sort of continuous scale here is that you have hairs in an area waving back and forth in resonance, if you will, with a particular frequency. One of the things we can run into, we'll talk about later, is hearing loss around that. All right, so you've got this cochlea, you got the hairs vibrating far around, you got this little round window here that helps minimize, helps balance out the pressure because you don't want pressure differences in here. And the eustachian tube is also here to help balance out pressure between the inner ear and atmosphere out here because the eustachian tube connects down to your throat and out to atmosphere. Um, you have your nerves, of course, and the vestibular canals, the vestibules. What do what what do the vestibules do? They here and connecting to all of your semicircular canals. Your semicircular canals are responsible for balance. There was a physicist once that thought he would be clever, and he stuck his head in a really strong magnet. And he did it slowly, and that was no big deal. And then he turned his head quickly. And all the fluid inside of these semicircular canals is ionized. And when he turned his head quickly, it caused the fluid in those canals just start flowing around all over the place. His brain couldn't handle it, and he passed out right away. Hearing loss. So there are a lot of different ways we can have hearing loss. We can have temporary hearing loss, we can have permanent hearing loss. Some of the more permanent hearing losses, and one of the reasons you wear protective air gear around either A, loud noises, or B, constant whines of a particular frequency. All right, if you got a constant whine of a particular frequency, then you're always pounding away on the little bitty hairs that go with that frequency right here in the cochlea. Well, you can wear out that little section of the cochlea from overuse. And so you lose hearing at a particular frequency, which can be problematic. Loud noises, in particular, constant loud noises or impact noises, they cause the eardrum out here, which is this nice little flexible membrane. They damage it and they cause it to build up scar tissue. And so as you get scar tissue built up on this, what happens? It becomes less flexible. And so the flexibility in the eardrum is another major way in which people lose hearing. There's also age-related loss to flexibility in the eardrum. And so as you get older, you can't hear as well. Why? Because your eardrum just doesn't have it anymore. Your eardrum just doesn't vibrate back and forth like it used to. All right, I pulled out a few auditory illusions for you. They're kind of cute. The one that integrates vision and sound is very interesting to watch, very instructive to see. The others are just cute little things. This was a pretty good recording. You want to hear headphones for that one. Um, but yeah, take a look at these, or take a listen to these, and a look. This one requires a look. Take a look at that one, and just pay attention to, you don't quite hear how you think you hear. And an interesting thing, all right, I'm going to do a little drawing. This is an aside. So you've got your brain. If I could draw, here we go. You've got your brain. It's got two halves that don't quite look like that, but there's your brain, all right? And you got your ear over here and your ear over here, and then you got eyeballs. Well, your eyeballs, whoa, attached to the occipital lobe way back in the back, all right? And your ears attach to the sides of your brain here. They don't attach to the same place at all, right? And so when you hear and see something, your brain has to take those signals and put them together because they're two separate signals. And there are actually things you can do to fool the brain and get its timing off. And there are some experiments that have been done with people where they would use a flashing light and a little button you have to press and a noise. And you can actually get people into a situation where they think the light flashed before they pushed the button, even though pushing the button turned the light on. It's really interesting. Things you can do in playing with the brain around how you hear and see and how that gets integrated in the brain. Okay, now onto the math bits, right? The decibel scale, a variable we use is beta. The units are dB or decibels. We'll run into intensity, I, which is watts per square meter. We run into a reference intensity for the decibel scale, I naught, which is 10 to the minus 12 watts per square meter. P, power is in watts, are joules per second. A is area, and R is distance, which typically in things we'll be looking at is a distance from a speaker. So who's the decibel scale named for? Give you one guess, and you better get it right. All right, Alexander Graham Bell. And it is basically a really simple relationship, right? We're taking a base 10 logarithm. So our intensity in decibels is 10 onto the log of our intensity in watts per square meter divided by I naught, this reference intensity. Units of watts per square meter are power per unit area. So we could also write this as just say this is power over area, right? And consider a 1 watt speaker. Let's think about this. 1 watt speaker, that's your power. Power is 1 watt. Sound radiates out from it in an almost spherical wave. And the area of a sphere is 4/3 pi r squared. This isn't always completely true, but it's a good approximation most of the time. Speakers can be more directional or less directional. And a purely omnidirectional speaker is 4/3 pi r squared. R is the distance from the speaker. So the intensity is 1 watt over 4/3 pi r squared. And I'm just going to rewrite it as power over the area. That's the intensity, is power divided by the area. So now you know the intensity from a speaker based on how far away from it you are. The power of the speaker divided by 4/3 pi r squared. All right, I'm going to write that a little more generally just by putting power up in place of the 1 watt. All right. power over 4/3 pi r squared is the intensity of a speaker when you're a distance r from it. 1 watt, by the way, is a lot, right? Why do we use the decibel scale? Now, these intensities are ridiculous because they're very loud, but it demonstrates what I'm after. A change in intensity from 1 watt per square meter to 10 watts per square meter sounds to the human ear like the same step as from 10 watts to 100 watts, even though the first one is just 9 watts per square meter more, and the second one is 90 watts per square meter more, right? We hear in a nonlinear way. We hear in a logarithmic scale. There are a lot of processes in the human body, both sight and sound among them, where we use a log scale for looking at intensity because that gives us what we call in physics a much larger dynamic range. If we were linear in this scale, our dynamic range would not be nearly as good as it is. Another way to write the equation for decibels ends up being beta is 120, pardon me, 120 dB plus 10 log times of the intensity, right? 120 dB plus 10 log I. Now, intensity is almost always less than 1, which makes this last term negative, and so you're almost always below 120 decibels. If we turn this around and we express the intensity in terms of the intensity in decibels, right? Intensity in watts per square meter, we get to I is 10 to the minus 12 times 10 to the beta over 10, or I is I naught 10 to the beta over 10. So 10 to the power of beta divided by 10. Because you might need them, let's cover, and I've already used them, right? Let's cover a few properties of the log. Log of A times B is log A plus log B. This is why we used slide rules back in the day, because we took multiplication and turned it into addition. Great handy thing to do. And we took division, log of A over B, and turned it into subtraction, log of A minus log of B. All right, so the slide rules were all about taking multiplication, which was hard to do in your head, and turning it into addition, and division, which was hard to do in your head, and turning it into subtraction. The inverse function, if you have x equals log of a, the inverse function is a equals 10 to the x. And that covers everything we're going to cover about the physics of hearing. We're going to have a bunch of problems about decibels. We're going to have some questions about how you hear. You need to kind of really think about it and think about all the consequences of what you looked at here in these slides in terms of how we hear. And good luck with all the problems.